Okay, the record is now on. So yesterday we talked about the phenomenon called shear lag. This happens when you cannot connect every element on the member. In this example, you see that what happened is that we can only connect one leg of the angle. So this leg is free in the air. That's why the force will not travel to this part of the angle. You see, it has to try to come to where the connection is as quickly as possible. That's the nature of the force. So when the length of the connection here is short, you see that it doesn't have a lot of room to maneuver itself from the centroid of the member to where the connection is. Okay, if the connection itself is pretty long, you will the force will have quite a better opportunity to maneuver itself into the location of the connection. Okay, you can think of yourself driving a car and you have to make a sudden turn, like this one. So the turn is not very clean, and this one is a clean turn. And if the connection is long enough, you see that you can shift the critical section away from the area where your material becomes ineffective. Okay, I can draw, oops, not this one. I can draw this picture again so that you can see more clearly. Okay, so this is the angle in that example, but I'm going to draw it in 3 dimensions. Okay, so this is how it looks like. We have an angle like this, and then you kind of weld it on one leg. So I can say that this is the outstanding leg. It stands out. We don't have any connection on it, no connection. So you can say that this is free in the air. So this is the leg that it's a bad grammar. So this is the connected leg. So in the end, you see that this is the element where you cannot connect, and normally we don't connect. Okay, because generally if you want to try to connect this angle to the support, so you're going to have a plate down here. So let's say this is going to be the area of the plate, down here. So let's say if I draw the front view, you're gonna see this picture, right? Like this. And then you see the baseline here as the cassette plate or anything. And this baseline is, of course, this blue piece. See, so that's the same thing. And I'm trying to be clear. So let's say if the bolt here is pink, you're gonna see the bolt here. Right? Because we can only connect one leg. We are not going to try to make the effort to connect this outstanding leg because it's a waste of money and it's a difficulty in construction work as well. So we don't do that. So this is your outstanding leg, OSL, okay? OSL, outstanding leg. So because of this condition, we now have the element of the outstanding leg that we cannot connect and we don't wish to connect, and we have another leg that is connected here. So you can say that this shear lag problem will occur because we cannot connect every element of the section. Okay, when I say element, I mean these 2 legs. So basically, if we talk about this angle, we have 2 elements: this outstanding leg and then this connected leg. Okay, So the outstanding leg becomes the element that we do not connect. So we're going to have the shear lag problem. All right. So the front view looks like this. The side view will look exactly like you have seen before. Okay. So the side view will look like this with the angle. Perhaps like that. So we have the angle thickness here. Okay. So this is the side view with bolts, maybe 4. 1, 2, 3, and 4. Okay. And do you want top view? I should say side view. And the top view will look like this. I've drawn this one, but I just want to do it again just to give you some clear understanding. Okay. So the top view may look like this with the plate going in like that. Now you're going to see the bolt like this, the bolts like this. Okay, so the most important idea is that the fact that you can only connect one leg means that you cannot connect the entire cross section to the support. So shear lag problem is going to occur. And because of this, the force that actually comes through the centroid of the member, believe it or not, the centroid of the angle is in the air. It's right here. But theoretically, correctly, this is where your force is. Sorry, where your force is through the centroid of the cross section. So this is a CG where the force is here. So when we connect, the force we have to try to travel from the CG to here, because we want to transfer the force from the member to the support, you know, a case like that. So the force is here. So this, if you look at the front view, you see that this is the distance that your force has to travel. In other words, it's the X bar of your cross section. Okay, and this becomes the length of the connection that gives the opportunity for the force to go through. And the shear lag factor can be calculated by simply using this formula 1 minus X bar over L. Is there any question? Oh, I kind of like this picture. You know, any question? If for any reason I can connect this angle or for both legs, there is no shear lag problem. Okay, so now we can go back here and say there's this table D3.1 in the specification telling you how you can handle the shear lag problem. Okay, so basically it states here that if the tension members where the tension load is transmitted directly to each of the cross-sectional elements, U is equal to 1, or simply put no shear lag problem. But see, they kind of like to use the word transmit. It seems like sending out signals, or I don't know. I kind of like transfer more. Anyway, so if the force can be transferred to each of the elements, so you see now you understand what the element is. Okay. Or I can rephrase this as if you can connect every element of the cross section, there's no shear lag problem. If not, we can use this formula to calculate the shear lag. Okay, and there are so many cases where they have recommendations on how you can handle the shear lag. For example, this is the plate, you know. They are weld 2 plates together. If you weld on 3 sides like this, drill on this side, and then on the end. There's no shear lag problem. But if you don't want to weld on the end, there is a formula for the calculation of the U. Say it depends on the ratio of this width versus the length. Okay. Next one. This is the way we connect the circular section in the old days. So we sort of try to put one plate through the middle like this, and then weld the plate through the circular section itself. If this is the way that your circular pipe is connected, they have a suggestion on how to calculate the shear lag. If this is how you want to connect your rectangular section or square section, again, they have the formula that you can use to calculate the X bar. These two, calculate the X bar, and then use this in our typical shear lag formula here. Okay? This one as well. Calculate the X bar, and then so on, and this as well. So I have to say that in the old days we do this a lot. Okay, because it's the best way that we could have done. You just put the gusset plate through the middle like this, or on both sides like this. But nowadays they have the three-dimensional laser cutting super mega smart equipment that can cut the section into anything, as long as you can give them the information of drawings. So we may not see things like this a lot anymore, because they can cut it's going to be difficult to draw. They can cut the pipe in any shape or form, and then you can just okay, weld them together at the junction in any way you like, things like that. So yeah. And if you can weld them through like that, I don't think you have to be concerned with the shear lag problem. It's ugly picture. Just gonna erase it. Okay. Anyway, more on this. Say, if you are lazy, you don't want to calculate shear lag. They also have numbers you can use based on these conditions. Anyway. But I think in general the formula itself it's not so difficult. Go back to this page. Just this. What you only need is, the information about the centroid of your member. Okay. And then the length of the connection should be given once you know how big your connection is going to be, how many bolts you're going to have, or how long the weld you're going to use. Okay. Now, one thing that you need to understand is this. In steel design, we have two ways to connect the members. First is by bolting, second is welding. So let me say right here that shear lag, or this EU factor, does not depend on how the member is connected. I mean, it doesn't matter if you use the bolts or weld. As long as all elements are not connected, shear lag must be considered. Okay, so that means if I don't use bolts for this one, if I instead weld this, I still have shear lag problem. Okay, let's say same stuff. But instead of using the bow, I weld this instead, but I weld only one leg because I cannot weld in the air for the outstanding leg like this. So shear lag still occurs. And ladies and gentlemen, occur is a verb, okay? Not is occur, okay? Shear lag still occurs, okay? So is there any question? Oh, all quiet. You know, let me go ahead and tell you one more thing. Whenever you connect the members in steel structure, the funny thing is that tension will not cause a lot of concerns in tension members. Compression will be the bigger issue for the members. However, on the contrary, tension will cause a lot more trouble with the connection because you can tear the connection apart where everything is connected. And compression will not cause a lot of trouble with the connection because you compress everything at the connection, so it will not fail. So for tension members, for the member itself, you can say that it's gonna fail because of yielding at cross section and rupture at the effective net section. Okay. In fact, when we talk about tension members and there are holes in it, there are two additional failure modes, but this will be mentioned in the connection part, so just gonna leave it here. But we will not consider this now. Block shear and bearing tear out. Block shear is when part of your tension member can fall off, and bearing tear out is a failure at the both holes. So this will be in the connection part. And when you consider the connection, which Ajahn Sutat will take over, you need to consider 4 of them. But let's say for tension members, to understand the aspect of the member itself, we are at these 2, okay, for tension members. For now. Okay. So now let's go back to this chapter 2. From time to time, we already passed this. We need to also check the subvisibility as I mentioned yesterday. And here, say it is a note here saying that for members designed on the basis of tension, the slenderness ratio L over R preferably should not exceed 300. R here is the radius of gyration, okay? If it becomes too slender, if your L over R exceeds 300, the transportation will become very, very troublesome. It's like nobody can handle it. When you put it on the crane trying to lift it, it's just gonna wobble. So this is the limit of usability for handling and transportation. And from time to time, we may need to check the deflection of your tension rod and so and so. If you can recall, this is a basic formula for calculating the elongation of your tension member, right? It's PL over AE, but instead of P, we use T. Okay, and say the calculation of deflection always depends on here, engineering judgment. Okay, you may from time to time are required to check the deflection of your tension members. And you better make sure that you need to check this or not, before you start working on your design. Okay, this is on engineering judgment, but for this, it's like a rule of thumb. You should always make sure that it doesn't exceed this one. Otherwise, you know, the construction phase will become very, very difficult. Okay. So, okay, that's it. It's just quite a few things because generally what you will find yourself dealing with for tension members is the design of the truss. And we have mentioned a little bit that you have so many configurations that you can choose to design the truss. But, you know, it has the effect. Let's consider this one. Okay. You know that the top and the bottom chords will handle bending moment. So if you put this truss into the analysis, you will see that as a result, I can say again that the top chord is compression and the bottom chord is tension, denoted by the color red and yellow. But what you should notice is that, well, generally the vertical web will be under compression because, you know, the load should come like this, right? There no doubt the vertical web should be under compression, but this diagonal web is under tension. However, if you invert this truss configuration into something like this, you know, on this one on the right instead of the one on the left, which I just showed in the previous picture, notice that here the diagonal web is under compression instead. And in compression, as I mentioned, that the steel member is going to have a problem with the, you know, buckling and so on and so forth. So preferably, if you could, you would want to handle tension rather than compression in terms of member design. So you see, the selection of your truss configuration will dictate how the structure is going to come about as well, because instead of designing this diagonal member, and you see the diagonal member is always longer than the vertical one, right? So instead of designing the long member to undertake compression, you want to design the longer member to undertake tension instead. So the configuration would, you know, yes, dictate how your design is going to be as well. And you should recall from mechanics of materials, the long column issue, right? The longer the compression member is, you know, the less load carrying capacity it's going to have. So that's it. Okay, so right here, see, if you choose the proper configuration, this, see, the long diagonal webs will have tension instead, but this will have compression. So now you see which configuration you should use, right? Okay, and, wow, this is the three-dimensional truss. Skip that one. You know, I used to design this one, stuff like this, when there was no three-dimensional computer program. We only, what we had, the best one we had was two-dimensional computer. So this one was really something, the three-dimensional truss. If you're interested in how I handle that one, you can ask later. Okay, so here is a part of the bracing system. So, yeah, of course, it's also a truss system. Okay, and this is the tension members. In the extreme, you know, I really like the one on the right because, you know, you put all the forces here, and then the reaction comes down here, supported by the cable, because both architects and engineers must have worked together and they understand the nature of the force. So they put everything in the middle and just, you know, it all comes down here. So when you put the support here, you know, all the cables will support tension. So because of that, you can have like small structure to support, you know, everything. So it's kind of cool, right? And this as well, you know, they this is called the suspension. This is the suspension bridge, if it's like this, okay? So because the bridge is now suspended from the cable, so the cable can be very small because the force is tension, right? Very good idea. Okay, so you have a lot of the things like that. And one last thing to show you, because Jessica and I were in pretty much the same era. So this is what happened in the US of A, you know, the collapse of the walkway that is supported by the rod. So the walkway used to be in the middle here. Yeah, that was what, this is after the collapse, but it looks like this, supported by the tension rod like that. Good idea, you know, just suspend the bridge, but then one day it collapsed. And it was found out later that this was the original detail. The tension rod going through the membrane, getting in like that. But during the construction, it was hard to do. So they changed the detail into something like this. So if, you know, you understand what's going on, you will understand the free body diagram of things. It's a simple detail like this, because if you are pretty good at free body diagram, you know, the fact that the thing that I always underline in the class, the free body diagram on the right is nothing, because it's a single thing. You have tension like this, right? But then on the right, because the detail becomes difficult, so they change the place like that. So your tension is here and then there. But what about here? You see, the forces on both ends do not coincide anymore. So here, this portion cannot take the torsion that occurs because the two forces do not coincide, and it wasn't designed for it. So it got torn apart and collapsed. And just so happened that, you know, when something bad is going to happen, the load would be full, right? So you see the number, 114 dead, more than 200 injured. So, you know, yeah, because sometimes experience does teach you something. And this is the country where, you know, they are very, 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 very good at engineering. And still some crazy mistakes do have happened in their country. And, you know, I remember this very well, because when I was taking the seminar class, they gave the one failure to each student to find the information about that and then present about the failure in the class. So each graduate student will get one failure incident and they study about it and then they talk about it in the class, just to raise awareness of, you know, what actually happened. So they are not afraid to talk about this, you know, unlike in some country in the southeastern region of Asia, where, you know, when the accident happens, they try to cover everything. You have to share it so that the community grows. Okay, I got the one incident where they cast all the floor, you know, the floor in a huge diaphragm, and then they lifted the entire floor to save time so that you don't have to cast concrete on site. They cast the entire floor from somewhere and then they lifted, and then just the equipment broke down, the lift something that collapsed, and then the floor just came down, and they got the progressive collapse of the, you know, floors coming together, bam, 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 coming down like that. So yeah, they try to see, they try to use technology, which would have saved time and money and lives, but sometimes but ignoring small details like this one, you see, wrong free body diagram, and that's it. Okay, so I think that's pretty much wraps up the tension members, and now we can go through the design example, and you guys can use this document. I already have everything for you. Okay, so we can now start working on here together. So let's say this is the first one. Okay, now you have the load. All right, you have the case where you have to select an H shape, and it's been decided in the beginning that we are going to use the SS400 material, and you have to select this member to carry dead load 15 tons and live load 45 tons. Okay, and the member is going to be 7.5 meters long, and in the first condition, a member is going to be entirely welded to the support. What does it mean? What does this mean? It means that we're not going to have shear lag problem because we are going to weld both the flanges and the web of the member to the support. In other words, we are going to connect every element of the members to the support. Okay, I can say this would mean that both flanges and web will be connected, so no shear lag. Okay, so far any question, folks? Any question? No? Okay, so let's go. Now this is your first design experience, I have to say. We are going to begin by knowing just the forces acting on the member. Let's say this is from the analysis. Okay, after the analysis, you now you know that your member have to carry this force. Okay, so let's say I can say step number 1 required. This is my required, okay, tensile strength. Let me do you want me to illustrate just ASD first or ASD and LRFD all together? Hello? Hey, are you still with me?
I think it's together is okay.
Together is okay, so fine. So let's say we are going to calculate the load combination. If you have only 2 dead load and live load, so if you check the load combination, which you should, if you have time and do some self-study, we only have 2 load combinations case. The first is total dead load. The second is dead load and live load. Okay, so no brainer that the dead load and live load case should govern. So in ASD, our load is going to be, let's call it PA. It's going to be simply 15 plus 45, that is equal to 60 tons. Okay. And you may want to say this is the service load. Okay. In LRFD, it becomes the ultimate load, PU. Now we have to factor the load. And the load combination factor for LRFD, mind you, this LRFD is the US based load combination in our country. The building codes is messed up the LFD load combination. For now, they don't have it. If they're going to have it in the future, I will not recommend that you use it, and I will tell you why soon. Okay, so we have 1.2 date load. Let me write this one for you. 1.2 date load plus 1.6 live load. So it becomes 1.2 15 plus 1.6 45. This turns out to be 90 tons. And I call this factored load. I have a lot of ants in the house now. Factored loads. So okay, so now we know the load. The next step that we want to do is just we are going to try to pick some section. So we can call this step prelim design. Now, so for the first time, I'm gonna try to write a full word again. Preliminary, yeah, design. So now we sort of know that say we're gonna have two failure modes. Okay, the yielding and the rupture. So let's say I'm going to try to pick up the section by check the yielding. Okay. So we're going to consider the first failure mode, yielding. And we know that the only universal design equation is that PA cannot exceed our design strength. Oh, I have to say ASD in front as well. And our design strength, if it is ASD, it is P nominal divided by factor of safety. And for yielding, our P nominal is FY AG, right? And then this, of course, divided by factor of safety. So from here, I can calculate the area that I would need, correct? So I can say area AG would now have to be equal to or greater than factor of safety multiplied by PA divided by FY. Correct? So now we know it's 60 tons. Change the unit into kilogram force. Yeah, I write the factor of safety in front. So let's move this so that you know what is what. Okay. Factor of safety is, of course, 5/3 or 1.67. And then because we are saying that we use SS 400, so FY is going to be 2,500 kilogram per square meter. So this gives me the area of 40 square centimeter. All right. Now, because of the special condition that we have here, it says that the member is going to be entirely welded to the support. So we can assume that there'll be no holes in it at all. So if I wish to, I can go ahead and check the rupture. Because in this case, no holes means the net area will be equal to the gross area, right? And because there is also the issue of welding every element to the support, so there's no shear lag. So I can safely say that my effective net area is just the my net area. Okay, so the same thing. I can say my PA or my AG should be greater than or equal to the factor of safety multiplied by PA divided by FU. Okay? But you have to be mindful that this is rupture, so that the factor of safety here is going to be equal to 2. Right? Force is the same. And then this time the FU is 4050. I use this number. If you use 4000, I would not say that you are wrong. Okay? You're free to use 4000. And I got 29.6 square centimeter. So now before I go into the LFD, I want you to notice a few things. First of all, when you don't have any holes or any reduction of the area, it's only natural that the rupture would occur after the yielding, right? Because if it's the same section, how can you pull something and it doesn't yield before it's going to rupture? So yeah, chances are your rupture will never govern, even though the factor of safety for rupture is higher, but so is the FU over the FY. A second thing I'd like you to notice how the factor of safety here, you see, it reduces the strength of your section. So when you move the factor of safety in trying to solve the equation, see how it increased the load now, you see? Because the old concept of ASD, it's about factor of safety. So that means you either reduce the strength of your structure or you increase the load by factor of safety. It's a simple concept of trying to increase safety to the structure. No more than that. Okay, it's just that simple. Any question? So from this, you will see that you only need to select the section with what? If you have two conditions, because of this. So in the end, it means that you need to select the section that has a cross-sectional area greater than 40, not just greater than 29.6. Okay, it has to be greater than 40. If you select something greater than 29.6, but not greater than 40, your section will not pass the yielding criteria, right? It has to pass both, so it has to pass the greater number. Okay? So, any question? Seems like nobody wants to talk to me at all in the design. So let me stop the record first.